What's up, everybody? It's Dan from SageMathTutoring.com, and I am here with another video for my calculus students review sheet, and we're going to go through problems number 7 through 12, and this is for a calculus final in university. Okay, so let's take a look. Sketch the graph of f of x equals x times radical x plus 2. So what we'll do is answer these questions one at a time here. So let's take a look at 7a. 7a says, what is the domain of this? Well, first of all, we know the domain is not allowed to be such that the number under the square root symbol is negative. Okay, so we need to make sure that all the x values on this graph are such that this radicand would be either 0 or positive. So one way of immediately seeing what the domain is to actually set that radicand equal to or greater than 0. And in doing so, we'd quickly see that x has to be -2 or greater. So that could be represented with this domain here, where it's from -2. And actually, it should be brackets for -2 all the way to infinity. So that is 7a. 7b, what are the intercepts? Well, the intercepts, first of all, there's the x-intercepts and then there's the y-intercepts. Now, the y-intercept is what you get when you set x equal to 0. Now, when you set x equal to 0 here, then y would be 0 because of this x right here. So therefore, one of the intercepts is the y-intercept, and that is 0, 0. Now, that also happens to be an x-intercept as well. Now, let's see. If we wanted to find other x-intercepts, one thing we could do is we could set y equal to 0 and then solve for x. And anytime I say y, just know that I mean, f of x, okay? So y and f of x will be interchangeable. So once again, we could set the y equal to 0 and then solve for x, and in doing so, we would, let's see, both sides, we could divide both sides by x. That would leave us with this. We could square both sides, and that would leave us with this, and then we could subtract 2 from both sides, and that would give us that. So it is true that the other intercept, in this case the x-intercept, would be at -2, 0. So I'm going to say let's piece that information together in the graph, actually. Let's at least plot those points. So there's a point here, and there is a point here. Okay, looking at part C, is there any symmetry? Well, there's symmetry if you perform the test to find out if there's symmetry, and that test would be a matter of plugging in -x for x. So what happens when we consider f of -x? Well, that would be -x times 2 times plus -x there. And that would turn out to be -x to -x. Now that is not odd nor even, because it almost seems like it's going to be the negative version of the original function. But it's not the original function because it says minus in there as opposed to plus. Had this been a plus sign, then it would be an odd function, and in that case, it would have been symmetric about the origin, okay? So there's no symmetry. All right, looking at D. Are there any asymptotes? Well, asymptotes would be present in rational functions, and this is not a rational function. and it would be present in a rational function where, for example, there's an x value in the denominator that causes the denominator to be 0, and therefore the rational function is undefined. So bottom line is this is not a rational function, so therefore there's no asymptotes. Now, it is the case that there are restrictions on the domain, which we already discussed, but there are no asymptotes. Okay, the next one, which is 7e, says find f prime of x. Well, f prime of x would be a matter of finding, of course, the derivative. And in order to find the derivative, I would use the product rule for this. I'm going to call g of x, x. I'm going to call h of x radical 2 plus x, also known as 2 plus x raised to the 1/2. And we are on number 7, by the way. And therefore, g prime of x is 1, and h prime of x is 1/2 times 2 plus x to the negative 1/2, and that is also known as 1 over 2 radical 2 plus x. So that's all true. And with regards to finding f prime of x, that would be a matter of using the product rule. So the product rule, in this case, should be a matter of plugging in content into these parentheses. Okay, so we're going to plug in content into those parentheses. Well, what's the content that belongs here? The content that belongs here is we're going to have g of x, so x. We could then have h prime of x here, which is this. So that's 1 over 2 radical 2 plus x. And then we are going to have g prime of x, which is just 1, times h of x, which is radical 2 plus x. And that turns out to be, at the end of the day, let's see, x over 2 times radical 2 plus x plus radical 2 plus x. So that is the derivative. Now, it's possible the teacher will want his students to consolidate this into a single monomial. So what we're going to do is we're going to ensure that we have like terms by multiplying the top and bottom by 2 radical 2 plus x. And that's going to be 2 radical 2 plus x underneath. And up top, it's going to be x plus 2 times 2 plus x. And that's going to end up becoming x plus 4 plus 2x, which is, up top at least, 3x plus 4 over 2 plus x. So that's the derivative. It's kind of a nicer way of saying the derivative. Okay, looking at the next part, where are the intervals of increasing or decreasing? So that means that we have to set the derivative equal to 0. So that's exactly what we're going to do. We're going to set this derivative equal to 0. So we'll say 0 equals 3x plus 4 over 2 times radical 2 plus x. Now, the reason we need to do that is because we need to find the critical numbers or the critical values. Now, When it's rational, like this, meaning there's a function on top and a function down below, really you could split it into two separate things. So we have this equal to 0, and then we're going to solve for x there, and we also have this set equal to 0, and we're going to solve for x there. Now with regards to the top one, x would end up being -4/3, so that is a critical value, and with regards to the bottom one, x would end up being -2, so that's a critical value. So what we'll do is we'll make our sine graph with those numbers represented. We have -2, and we have -4/3. Now, -4/3 is really -1 1/3. So we do know for sure that it's going to be to the right of -2 on the number line. We also remember, hopefully, that there is that domain restriction here where the domain is all values greater than or equal to -2. So there's going to be nothing here on the left. And what that means is that there's only two sections we need to investigate. We need to investigate this section here, and we need to investigate this section here. So let's do that. When we look at this section here, which would include 0, let's plug a 0 into the derivative. So that would become 4, which is positive, over another positive number, because if you plug 0 in there, the bottom would be positive as well. So that's going to be a positive over a positive, and therefore we are looking at a positive slope there. So the graph is increasing in that interval. With regards to this green section, -4/3 is really -1 1/3. -2 is obviously -2. So a number that would be between -1 1/3 and -2 is -1 1/2. So we could test that, and that is -3/2. So if we plug -3/2 here, you're going to get a negative number. Okay, so 3 times -3/2 plus 4 would end up being a negative number. And then down here, we would have 2 times radical 2 plus -3/2, which is really the same thing as 2 minus 3/2, which is really the same thing as 2 minus 1 1/2, which is really just radical 1/2. So the bottom line is the top would be a negative number, and the bottom would be a positive number. And then that would lead to a negative decreasing situation. So we know that this graph is decreasing from -2 to -4/3, and it's increasing from -4/3 to infinity. With regards to local maximum and minimum, well, there's no maximum because it shoots up forever. Okay, so there's no maximum because it shoots up forever, and there's no particular confined interval that we're taking into account. We're taking into account the entire domain itself, and it goes up forever, so therefore we can't say there's like an absolute maximum. Now, had we only paid attention, for example, to the interval between -2 and I don't know, -1 or something, it could have been the case that the maximum is right here, the local maximum was right here, but since we're dealing with the entire domain as opposed to a confined interval, there's no absolute maximum in this case. Now, there is a minimum for sure. This is most definitely the lowest point on the graph. There's no question about it because it's a downward slope and then it's an upward increasing situation after that. So the minimum would be whatever the y value is when x is -4/3. Now, that could be found by plugging -4/3 into the original function. So let's do that right now. F of -4/3 is -4/3 times 2 plus -4/3, that's really 2 minus 4/3. So investigating that, we are looking at, let's see, -4/3 times, that would be 6/2, or 6/3 rather, 6/3 minus 4/3, and that is equal to -4/3 times 2/3, and that would end up being that number. Okay, that would end up being that number. Well, I will say that radical 2 over 3, that could be split into this, so that's a possibility. The teacher might want you to do that. Then the teacher might want you to rationalize the denominator, so that would become, down below, it would become this 3 times, now when you multiply these two together, that's going to become 3, so it's going to become 3 times that 3, which is a 9, and then up top, we're going to have negative 4 times radical 6. Negative 4 radical 6. It's likely the case that the teacher would be happy with that as the minimum. Now, if the teacher wants the actual coordinates of the minimum, then it would be negative 4/3 because that's the x value we plugged in. And then the y coordinate that we just discovered is negative 4 times radical 6 all over 9. Okay, so that is the minimum, yada yada. What else are we looking for? Find the second derivative rather of f of x. So the first derivative was given here. So if we take the derivative of that, that's going to be a quotient rule scenario. So I'm going to write that up here. So f prime of x was 3x plus 4. So f double prime of x is going to turn out to be, a fraction type situation. And we're going to use the quotient rule. So we'll extend that. It's going to be sort of big parentheses situation. And what goes down below? Oh, I should have, well, I don't know why I forgot that. That's kind of funny. So the denominator of the first derivative is actually 2 times radical 2 plus x. Whoops, 2 times radical 2 plus x. Okay, so that's the number that goes down here. It's going to be 2 times radical 2 plus x. And then it's going to go here. We're going to have 2 times radical 2 plus x. And then it's going to be a matter of multiplying that times the derivative of the original numerator, which is 3. And then we have to go on a mission over here to find the derivative of 2 times radical 2 plus x. So I'm going to do that off to the side. We're going to imagine that the function called 2 times radical 2 plus x is h of x. And if we were to find h prime of x, well, it might be helpful to first reconceptualize h of x as 2 times 2 plus x raised to the 1/2, and therefore h prime of x would end up becoming, bringing the 1/2 out front using the power rule. That would become 1 times 2 plus x raised to the negative 1/2. Now I'm not going to write the 1 because there's just a 1 there. There's an invisible 1 there. And using the chain rule, we would have to multiply that times the derivative of what's inside the parentheses. Now, it turns out that the derivative of what's inside the parentheses is just 1, actually. So there's an invisible 1 over here as well. And rewriting that in a way that looks a little better would be 1 over radical 2 plus x. So that's the derivative of that one. So we're going to put that here. 1 over radical 2 plus x. And the original numerator goes here. So we're going to put 3x plus 4. So that's the second derivative. Now, it's likely the case the teacher will want more simplification to take place there. So let's take a look. We're going to do a little divider, and investigating, we would have 6 times radical 2 plus x. Minus the entire quantity of 3x plus 4 over radical 2 plus x. And that's going to be all over, let's see, that would be, well, this is something we could actually square. So that would become 4 times 2 plus x. Then, going further with it, we on the bottom would certainly have 8 plus 4x. On the top, if we were to force these terms to have the same common denominator, we could then, in order to do so, we could multiply the first term by radical 2 plus x over radical 2 plus x, and in doing so, we would end up with, let's see, it would be, certainly the common denominator would be radical 2 plus x. So I'll just kind of get that over with for now by writing that. I'll extend this a little bit more as well. And then it would become 6 times 2 plus x minus the entire quantity of 3x plus 4. So if we were to go further with that, that would become such that the denominator is still 8 plus 4x. Down here, we would have 2 plus x, and then here we would have, let's see, this would become 12 plus 6x minus 3x minus 4. These would combine, giving us 3x. These would combine, giving us positive 8. So let's represent that over here by writing, let's see, positive 3x plus 8. Now we have a fraction over a non-fraction. Whenever that's the case, you could simply multiply the two denominators. So we would end up with 3x plus 8 all over the quantity 8 plus 4x times radical 2 plus x. Now, that is true so far. However, there might be opportunities to simplify further. For example, even though we had distributed earlier to get 8 plus 4x, it might be worth checking to see what happens if you factor out a 4. So it would become a 4 times 2 plus x, and that is still being multiplied to radical 2 plus x. Now, it's the case that the denominator could also be rewritten as 4 times 2 plus x to the first power times 2 plus x to the 1/2 power. And it's the case also that 1 is really 2 over 2. So therefore, what we could rewrite this as is 3x plus 8 times 4 times 2 plus x to the 3/2 power. And we could also rewrite that as 3x plus 8 all over 4 times the cube root of 2 plus x squared. Okay, so that is the second derivative. Okay, where were we? Good Lord. Okay, concavity and points of inflection. Okay, well, our second derivative is all the way over here. So I'm going to bring it over. Thank God for that feature. So that's the second derivative right there. And let's find concavity and points of inflection by finding the critical values associated with the second derivative and then setting up another sign chart. So when you set this equal to 0, it would be that, and when you set this equal to 0, it would be this, 2 plus x squared. And when you solve the top, it would be negative 8 over 3. And when you solve the bottom, that would turn into x equals negative 2. So those are the critical values associated with the second derivative. Setting up a sign chart now, we would have -2, we'd have -8/3. -8/3 is actually to the left of -2, and we also know that it's the case that the domain of this is from -2 all the way to infinity. So it doesn't make sense for us to take into account any x values of -8/3. So actually we could disregard that and focus only on this partition here. This partition here. Now, with regards to this partition here, we could test any value, plug it into the second derivative and find out if it's going to be positive or negative. So let's test out 0. If x was 0, you would have 8 over what is ultimately going to be a positive number. So therefore, this is concave up. Okay, so now they want us to sketch the curve. After all that whole journey, now they want us to sketch the curve. Well, we know the domain goes from -2, blah, blah, blah. All right, we know it's concave up. You know, the whole thing is concave up. We also know it's decreasing between what? What is it decreasing between? Let's see. It looks like it's decreasing between -2 and -1 1/3, and then it increases after that. So in my view, that's a lot of good information. We also know the minimum. So this point is on the graph as well, -4/3 and -4 radical 6/9. So the radical 6 is approximately 2 point something. Let's say that it's like 2.5. It's not 2.5, but let's say it is 2.5. -4 times 2.5 is -12-ish, right? I'm pretty sure. Is that right? -4 times 2.5. No, that's -10-ish. So -10/9 would be something like just over 1, or just over -1, or we could say just less than -1, -10/9. Just under -1. So that is good information. -1 1/3, comma, -10/9. So that would be somewhere around here, -1 1/3 and -10/9. So that would be like right there-ish. Okay, something like that. And we also know it's concave up, so it's going to be swooping down, then it's going to go up, and then it's going to go up forever, like that. So that is that one. Okay, problem number 8. Similar situation where we're going to find the domain. So A, find the domain. Domain would be all values of x except for the values of x that would ever cause the bottom to be 0. Now it's the case that there are no x values that would ever cause the bottom to be 0, because whatever x is going to get squared, and that's going to result in a positive number, or 0. And then it's going to become that number plus something, plus a positive number. So it's going to always be a positive number down in the denominator. So the domain is going to become -infinity to +infinity. Now the range, we don't care about. So that is A. B. What are the intercepts? Well, the intercepts are the places where the function crosses the x or y axis. So we know it crosses the y-axis when x is 0. So when x is 0, it turns out that y is 0. So we know that 0, 0 is a point on this particular graph. We also know that this would be not just a y-intercept, but an x-intercept. Now, with regards to the other x-intercepts, you could find that by setting the entire equation, or function rather, equal to 0, and then solving for x. Now, it turns out x would just be 0. So it looks like there's only one intercept here, and it's at 0, 0. Okay, looking at part C, state symmetry, if any. So let's perform the test. We'll see what happens when we substitute negative x in for x. That turns out to be 8 times negative x all over negative x squared plus 4. And that turns out to be negative 8x over x squared plus 4. So it turns out this is an odd function, so it's definitely symmetrical about the origin. Okay, so I'll just write origin there. So that's an odd function. Okay, find any asymptotes. Now, asymptotes, vertical asymptotes will be found by noting any x values that would cause the denominator to be 0. Now, there's no x value that would cause this denominator to be 0, so therefore there are no vertical asymptotes. However, there is a horizontal asymptote. So what we have here is a degree of the function down below is larger than the degree on the function of the function on top. So therefore we have a horizontal asymptote at y equals 0. So just write that. So in other words, there's a horizontal asymptote like there. Okay, with regards to E, find the derivative. Well, I would say the quotient rule would be a good idea once again. So we're going to have f prime of x. That's going to equal something squared for sure. And there's going to be something times something minus all this stuff. So what belongs down below? Well, the original denominator, x squared plus 4, and that's going to go right here as well, x squared plus 4. Up top, or I should say right next to x squared plus 4 is going to be the derivative of the original numerator, which is 8. And then we're going to have the derivative of the denominator, which is 2x, times the original numerator, which is 8x. So at that point, we can simplify further by distributing that 8. It would be 8x squared plus 32 minus 16x squared, and that will be all over x squared plus 4 squared. We're going to leave that one like that for now. Looking here, we would have negative 8x squared plus 32 all over x squared plus 4 squared. So that is the derivative. Then they ask us to find the intervals of increasing or decreasing. So that's going to be a matter of finding the critical values associated with these, the numerator and the denominator. So it's going to be negative 8x squared plus 32 equals 0. We're also going to consider this one where it's x squared plus 4 squared equals 0. Then this would turn out to be x squared equals 4, and that would turn out to be x equals plus minus 2. Over here, we're going to have, let's see, yeah, there would be no solution here because after taking the square root of both sides, we'd have x squared plus 4 equals 0. Then we would subtract 4 from both sides. We'd have x squared equals negative 4. And we don't want to be taking the square roots of any negative numbers anytime soon. So these are the values that we're going to want. Now, I want to remind myself, what was the domain? The domain was all real numbers. Okay, so that's cool. So at that point, we want intervals of increasing or decreasing. Well, first you got to find the critical values. We already did that. The critical values are positive 2 and negative 2. So therefore, we have to write a sign chart. I'll do it over here. Why not? Negative 2, positive 2. We have this area to take into account. We have the red area to take into account. And we also have the blue area to take into account. Let's look at the middle. That would be 0. When we plug 0 into the derivative, what do we get, positive or negative? Well, it would be a 32 over a positive number, so that's certainly going to become positive, so that's going to be a positive slope there. It is the case that when we plug in something greater than 2, for example, 3, that would be negative 8 times 3 squared, which is negative 8 times 9. and that would be a negative 72 plus 32, which would give us a negative numerator. Now the denominator is definitely going to be positive no matter what, because whatever's in here gets squared. So that's going to be a negative over a positive, therefore the whole thing is going to be negative, so it goes negative there. With regards to this section here, if we tried out negative 3, that would once again actually result in that negative number up here, negative 72 plus 32. So that's a negative number up here over a positive number down below. So that would also be a negative decreasing scenario. So I would mention that to the teacher. You might want to use interval notation. It decreases from negative infinity all the way up to negative 2, not including negative 2. It also decreases from positive 2 to positive infinity, not including positive 2. And it increases from negative 2 to positive 2, not including either of those. Okay, now they're saying find local maximum minimum values. Well, the entire domain is negative infinity to positive infinity. So really what we're doing is we're trying to find maximum and minimums just in general. It is the case that there's a horizontal asymptote at y equals 0, which means that as x gets infinitely large, it approaches that asymptote. As x gets infinitely small, it approaches that asymptote as well. And as we look at this scenario, what that means to me is it's worth checking to see if that's a minimum. If that's something that's less than 0, then that's going to be the actual minimum, because over here, the graph approaches y equals 0. And over here, the graph approaches y equals 0 as well. So that could be a maximum if that's greater than 0, if that makes sense. Okay, so if that's less than 0, if the y value associated with the x value of negative 2 is less than 0, and if the y value associated with x equals positive 2 is greater than 0, then that could actually be a maximum, and this could be a minimum. So let's see what happens when you plug in negative 2 into the original equation. Well, if you plug in negative 2 into the original equation, it would become, let's take a look, it would become negative 16 over, and negative 2 squared is 4, so it becomes negative 16 over, looks like it would be 8, so that's negative 2, right? Negative 2. So it is the case that the point negative 2 comma negative 2 exists on this graph. And if you were to plug in positive 2 into the original function, you would also see that that would be positive 2, positive 2. That exists on the graph as well. Now, negative 2 is a y value that's less than the y value of 0. Positive 2 is a y value that's less than the y value of 0, which is the horizontal asymptote. So I would say that this is a minimum and this is a maximum. Okay, what is next? Find second derivative of f of x. Well, we already found the first derivative. It's here. So let's find the second derivative now. So it would be second derivative. That's going to be a quotient rule scenario as well. And when we use the quotient rule, it's going to be something squared down below. That's going to be up here as well. And we're going to be subtracting an entire quantity of something right there. Now, what goes inside? Well, it would be x squared plus 4 squared right there. That's going to go up here as well. Let's put the 2 there. So it's x squared plus 4 times the original, actually the derivative of the numerator, which is negative 16x. And then we're going to be multiplying the derivative of this bottom part right here. Now, what is the derivative of x squared plus 4 squared? Well, we could do that off to the side. Imagine we call that function g, x squared plus 4 squared, and finding the derivative, we would have the 2 out front, we'd have the x squared plus 4, and then we'd have to multiply that by the derivative of what's inside here, so that's 2x. All right, so then we have 4x times x squared plus 4. Now, even though we're trained to sort of distribute that I am seeing how there is potentially an opportunity to have a common factor up here of x squared plus 4 with this x squared plus 4. There's also an x squared plus 4 down below. So with experience, you might end up having the foresight to see that actually you might want to leave it like that. Okay. So therefore, I'm going to put that there instead. We're going to have 4x times x squared plus 4. And that's going to get multiplied to the original numerator. Now I'm actually going to write this original numerator in the reverse order just because I don't really want to deal with like a negative 8x squared as the first term. I don't know. I prefer it to be this. So I think right out the gate, it's obvious that there's this like GCF going on of x squared plus 4, okay? So I think it'll be helpful to factor that out because there's an x squared plus 4 down below as well. Let's also get this over with. These 2's could multiply together because that's a law of exponents. If you have a power raised to another power, you can keep the base but multiply the exponents. So therefore, this is going to become a 4 up there. Now, should we factor out the x squared plus 4? That would be smart. I'm going to use brackets. This term divided by x squared plus 4 would just simply be x squared plus 4, only one of them though, times negative 16x, and then it's going to be minus 4x times 32 minus 8x squared. Then we can most definitely make that cancellation, and it would be to cancel that, to cancel the 4 and turn it into a 3. At this point, I would distribute stuff, okay? Now, I'm going to go ahead and distribute this now, right here, just to save space. We're looking at negative 16x to the third minus 64x. And then over here, it would be negative 128x plus 32x to the third. Now, let's think about this. The x cubed terms are clearly like terms, and the x terms are clearly like terms. So I'll do a little divider here so we're not distracted by that. So the green triangle is a like term with the green triangle. The blue square is a like term with the blue square. So I think what I'd like to do now is go ahead and just combine like terms up top. Now that's going to result in 16x cubed. Negative 64x minus 128x is going to become negative 192x. And then we have x squared plus 4 cubed down below. It's certainly the case there is some kind of a GCF. They're both even at the end of the day. So at the very least, you could take out a 2x. They both have x in them as well. But it is the case that the GCF is 16x, actually. So we're going to have 16x times x squared minus 12. And that is the second derivative. Wasn't that awesome? I feel like it's just heaven. Heaven on earth. Okay, so we satisfied 8h. Now we want to know what's the concavity, what are the points of inflection? Well, as you remember, that's going to be a matter of setting this thing equal to 0, finding those critical values. And in this case, you could really kind of go off and do that splitting technique where it would be 16x times x squared minus 12. That equals 0. The other equation I could set up is x squared plus 4 cubed equals 0. When it comes to this one, we know that if x was 0, then the whole thing would be 0. When it comes to this one, we can tell that if x was plus minus 2 radical 3, then that whole blue equation would be 0 as well. So if you have to kind of go off to the side and solve that separately, that's fine. Over here, there'd be a moment where we'd have to cube root both sides, and that would leave us with x squared plus 4 equals 0. We'd then have to subtract 4 from both sides. We'd have x squared equals negative 4, but at that point, there's nothing we could do there because you can't take the square root of a negative number. That would result in an imaginary number, and we are only looking for real numbers in this case, okay? So we have actually 3 critical values. We've got negative 2 radical 3, 0, and positive 2 radical 3. So we do need to find the concavity and all that stuff. So we're going to have our sign chart, right? Sign charted up. We have this region to take into account. We have this region to take into account. We have this region to take into account. And we have this region. Starting with the green region, it would be a good idea to figure out what is a number that's actually less than negative 2 radical 3. Well, negative 2 radical 3 is negative 2 times 1 point something. So it would be safe to say something like negative 5 would work. So imagine we plugged in a negative 5 here. Well, we'd have a huge negative number, negative whatever, but that would be negative. Negative 5 times 16 would be a huge negative number. And then you would have 25 minus 12, which is a positive number. So the numerator would be negative. Now, if we had a negative 5 down here, it would turn into a positive number. We'd be adding 4 to a positive number, and then all of a sudden we'd be cubing that. So the denominator would be positive as well, meaning we'd have a negative numerator because negative times a positive is a negative over a positive, so that's going to be negative. Now, since it's negative, it's going to be concave down. Now, what about negative 1? If we were to choose negative 1, which is in the red region, we could do that. So I'll get rid of this stuff real quick. Okay. So if we were to choose negative 1, this would be a negative number, of course. And this would be another negative number because negative 1 squared is 1, minus 12 will give us a negative number, and then we would have a positive number down here. So we'd have a negative times a negative, which is a positive, and a positive over a positive is a positive. So that would be concave up in that case. Continuing on, if we were to choose a number like positive 1 over here, why not, you know? So that would be positive. This would be negative if we were plugging in positive 1, and this would be positive. So once again, we will have concave down. And looking at the next region, the yellow region, we could work with positive 5 this time. We had worked with negative 5 over here. We could work with positive 5 this time. So that would be some huge number, which is positive. And then it would be 25 minus 12, which is positive. And then we would have a positive down below. So we have a positive times a positive, which is a positive, over a positive. So ultimately, it would be positive and therefore concave up. So if you were to write, concave up, you could say something like from negative 2 root 3 to 0 union sign from positive 2 root 3 to infinity, concave down. I'm not going to write it, but That would be negative infinity to negative 2 radical 3, union symbol 0 to 2 radical 3. So that is the information. So let's piece together our findings. Okay, we're going to piece it together. Well, as a reminder, the domain goes from negative infinity to infinity. It definitely goes through the origin. That is apparently the only intercept. So we're going to put a red dot there. I'll blow this up a little bit. Okay. So it's also the case that, let's see, symmetry is symmetrical about the origin. So it might be something like that. There is the horizontal asymptote at 0. We took the derivative and we could use the derivative to figure out where is it going down, where is it going up, and then down again. So it must be, since it's going up and then down again, and there's an asymptote, that means it's probably something where it goes down and then up and then down again. Okay, so that's something to take into account. Now, the reason I say this is because the asymptote, the end behavior, as it goes, to the left forever, it gets infinitely close to the x-axis without going over. And we know it's going up though, right? It's going up towards that asymptote. So that means it's got to be going like that, right? The end behavior over here is going down towards the asymptote. So we know that it's got to be kind of like that. And then it goes up here sort of in between -2 and 2. So that means there's some action here where it goes up like that. Okay. Now keep in mind, you can cross the horizontal asymptote. The horizontal asymptote has more to do with usually end behavior. I think maybe even always end behavior, where the horizontal asymptote basically is a dotted line that the graph approaches as x gets infinitely large in the case of horizontal asymptotes, or x gets infinitely small to the left in the case of horizontal asymptotes. So with regards to the graph, we have our suspicions. It looks probably like this, but then we could double check the concave up-down stuff. So let's do that. We're going to bring this over here. We're going to investigate this situation. So -2 and +2 are critical values where it changes direction. But we also know about the fact that it's concave down here, concave up here, and so on. So let's see. Therefore, there's some action happening with -2 radical 3, and +2 radical 3, also 0. So we already sort of have 0 marked out. We know it passes through there. -2 radical 3 might be around here. +2 radical 3 might be around here. And yes, so we know this is not the real graph, but we know it goes up here. We know it's going down here. We know it's going down here. So I feel very confident that it would be something like this, because right now it's concave down. But then right there, it goes up. And something like this, I'll just try to make it symmetrical. And it's sort of like that. Now, what did I do? I took into account the direction changes. That's the first thing. Okay, now, by the way, I don't know if this is the minimum here. As far as the Y values go, I'm not really sure. We could check that, actually, but I don't want to check it just yet. And probably we should check that. So, but nonetheless, let's just get clear on the sort of curve. It would be true that I did honor this situation, didn't I? I also honored the fact that it goes through the origin. I also honored the fact that right here it's actually concave down. It's kind of like a downward shape U until this moment. Now it's an upward shape U, but that changes at 0 as it should, and it becomes a downward shaping U until it gets to this moment where now all of a sudden it's sort of an upward shaping bowl that you can pour water in. Okay, something like that, where the water would stay instead of just rolling down off the side. It would actually catch here because it's an upward shape U. So that is good. Now, did I take into account minimum and maximum? Did they even ask me for the minimum and maximum? I don't know. Yeah, they did. Okay, so we have that information. That's part G. Yeah, they did. We found that before. That's -2, comma -2, and +2, comma -2. So I will fix that right now. We are looking at a curve that actually looks a little different. We're going to make it a lot nicer. Watch this. When in doubt, just plot the darn points. We know this point's on there, so just plot it. We know this point's on there, so just plot it. And then it would be like this. Direction change. Boom. Okay. So that's it. That's the answer. That should be the answer. Pretty sure. Pretty sure. Anyway, that was not very fun, but moving on. Okay, so for problem number 9, sketch the graph of this whole thing. What's the domain? Well, the domain could be anything in this case because it's not a rational function. There's no functions, or we could say x variables in a denominator anywhere. With regards to the intercepts, well, the first thing you should ask yourself is when x is 0, what does y equal? And I think we can agree that when x is 0, y equals 2. Now, I ran into problems when I attempted to find out what x equals when y is 0. I discovered that when you set this equal to 0, there was no non-advanced way to find out the value of x. Now, in the comments below, if I'm mistaken about that, let me know. But I don't see any opportunities to find any rational roots here. So the rational root theorem doesn't seem to work. And when I plugged the value in to Desmos, when I plug this into Desmos, I see that there is an intersection, an x-intercept at approximately 0.771. So that is an interesting situation because there is a way to get that x-intercept, but it features a process that's very much beyond the scope of what my student is learning in her current calculus course. So that's something I would encourage her to sort of talk to the professor about. Perhaps there's a way that I'm not aware of with regards to how to find the x-intercepts here. So in the comments below, if you have any ideas, just let me know. With regards to the symmetry, there is no symmetry when we plug in -x for x here. It would not result in the same original function, and for that reason, it's not an even function. And when we plug in -x, it does not result in the negative version of the original function either, so therefore there is no symmetry. No asymptotes either. And f prime of x is, I'd say, probably pretty easy. I'll just replace this with f of x here, and we'll do f prime of x underneath. So finding the derivative, not too bad, right? So we are looking at -2 minus 3x squared. Of course, they're going to be asking us where the intervals where it's increasing or decreasing. So for my student at home, of course, just remember you set that equal to 0. And you find your critical values first. And then we would have an interesting situation, actually. So if you look here, -2/3. It would be an interesting situation where you'd have to take the square root of a negative number. So what that means is there are no real critical values. And what that tells me is that this graph is either decreasing forever or increasing forever. So all you really have to do is take the derivative, just find any value to plug into the derivative, and find out whether or not it results in a positive or negative number. And if the result is negative, then this graph decreases forever at all, over the entire domain. And if the result is positive, it means this graph increases across the entire domain. So when I plug in 0, which is a number, why not? We can see when I plug in 0 to the derivative, not the original function, but the derivative, we can see that it results in a negative number. So this graph is decreasing from negative infinity to positive infinity. All right, local maximum and minimum. Well, if it's decreasing the entire time, then there's no maximum, no minimum. We don't count infinity as a maximum, and we do not count negative infinity as a minimum either. So we can say none there too. So let's see. No. Okay, find f double prime of x. Well, here is the first derivative. So if we take the derivative of that, we would end up embarking on this journey where it would be negative 6x. So that is the second derivative. Pretty easy, actually, right? Then we want to find concavity and points of inflection. Of course, we're going to be setting that equal to 0. And in this case, we do certainly have a critical value where x equals 0. And therefore, if we want to find concavity and points of inflection, we could then plot that critical value and test out this region, test out this region. So if I was to plug a negative number like -1 in for x of the second derivative, that would result in a positive number. So what that means is it's concave up here. And if I was to plug in a positive 1 from this region into the second derivative, that would result in a negative number. So that's going to be concave down. Now the actual point of inflection, it would be a matter of plugging 0 into the original function, not this function, but the original function right here. So for my student at home, whenever you're doing the sign charts, just remember if you're testing a region, plug it into your current derivative, whatever derivative you're working with. If you're testing one of the critical values to find either a point of inflection or to find local maximum and minimum values, you take the critical value and you plug that into the original function. So with regards to the point of inflection, if I plugged 0 in for x at the original function, then it would be the point 0, 2. So I'm going to write point of inflection is at 0, 2. So that's important. And then we're ready to sketch the curve. So, well, it certainly goes through point 0, 2, right? So we know it goes through this point. What else do we know? We know it's concave up here and concave down here. We also know it decreases the whole time. So something like I just traced is feasible, okay? Now, before we actually draw the curve, we could get clear about the intercepts. Well, one of them is at 0, 2. So not only is 0, 2 a point of inflection, but it's also the y-intercept. And also 0.771, comma 0. So that would be right around here. So yeah, it looks like this thing would be something like this-ish. Okay. Something like that. All right. Notice how it's decreasing the entire time. It's decreasing the entire time. It's concave up in this region and it flips to concave down in that region. So I'd be comfortable with something along those lines. Okay, so the next problem is problem number 10. Let's see. Farmer with 2,400 meters of fencing wants to enclose a rectangular plot with the borders on a river. If the farmer does not fence the side along the river, what is the largest area that can be enclosed? Sometimes it's good to draw the situation. So I'm going to draw a river. Yay, river. And the fence is like along the river, and we're only using the black segments there. So let's see, what is the largest area that can be enclosed? Well, we could call this the width, we could call that the length, we could call that the width. And we know that without question, since the farmer has 2,400 meters of fencing just in general, we know that 2 times the width plus the length equals 2,400. And we want to maximize the area that could be enclosed by this particular fence. So whatever is getting maximized is the thing that you're going to have to take the derivative of. Or we could say whatever's getting minimized is the thing you're going to have to take the derivative of. So for example, in this case, we're going to be maximizing area. Well, the area will be length times width, right? And we're going to have to take the derivative of that. Now, it's often the case with these kinds of problems that you need two equations at least that feature, the information from the problem. And one of the equations also has to be an equation pertaining to whatever it is you're trying to maximize or minimize, which is what we have here. We're trying to maximize area. So we've already satisfied that, but then it's often the case that you're going to want to only work with one variable to make your life easier. And that's where the other equation comes into play. So for example, we could take the top equation and solve for L in terms of W. And then we could substitute that in to the area equation. So we know that really L is 2,400 minus 2W. And multiply that by W. We could actually distribute, and you would end up with that. Now, that is something where I would take the derivative of the area in that case. So it'd be 2,400 minus 4W. So at that point, if we want to take the next step, we would have to set this equal to 0. Understanding why this works is kind of cool and interesting, but seeing as how the test is coming up, I think it's going to be a little bit more important to just understand how to do it. And notice how it's very similar to a lot of the stuff we were doing before. So 2,400 divided by 4 is going to be 600. And there you go. So the width should be 600. Once you have the width, you could plug it into this one, and you could very quickly see that the length is going to be 2,400 minus 2 times 600. So that's going to be 1,200. So those are the dimensions at least, but let's be clear what they're asking. What's the largest area? So you would actually have to multiply these to get the largest area. And 1200 times 600, well, first of all, there's going to be 4 zeros. And 12 times 6 is 72. All right, so 720,000. And since it's area, it would be meters squared. Okay, problem number 11. A rectangle has its base on the x-axis and its upper two vertices on the parabola, yada yada. What is the largest area of the rectangle can have, and what are its dimensions? Well, I would definitely draw that sort of situation. Upper two vertices on that. Okay, so that's a parabola. It's an upside down parabola with this sort of y-intercept right there. And based on the x-axis, what is the largest possible area? So you are going to have some triangle like this. And just keep in mind that the distance from here to there we could call x. Okay, and you know, this is also going to be the same distance x. So we know that with regards to the actual rectangle, the entire base, therefore, and maybe we could even call this the length, is going to be 2x. We also know that the height is going to be the height of the parabola. Now, the height of the parabola is given by this equation, because one way of seeing this equation is essentially saying the height of the parabola depends on x. The height of the parabola is whatever this turns out to be. All right, so I'll say it again. The height of the parabola is this. So what I'm going to do is literally call this height, also known as, we could say, the width or whatever, that. Okay. So we want to know what the largest area of the rectangle could be. I think that's what they mean. And what are its dimensions? Well, the good news is since we constructed it this way, we could go ahead and follow through with finding the derivative of the area function. So the area is going to be, length times width. So that's going to be 2x times 12 minus x squared, right? And if we were to simplify that further, it would be 24x minus 2x cubed. And at that point, we're ready to go ahead and find the derivative. So we're looking at 24 minus 6x squared. And if we were to set that equal to 0, then it'd be amazing. 0, 24 minus 6x squared. X would be plus minus 2. So we can disregard this negative one because we are dealing with, it wouldn't make sense, like if we're considering an actual rectangle, just disregard the XY coordinate plane. In reality, we're considering an actual rectangle that has a particular size. So it makes sense to disregard the negative too, because it wouldn't make sense for a length to be negative, if we're dealing with an actual rectangle. So we can disregard the negative. And at the end of the day, x equals positive 2 for this rectangle, and therefore we are looking at a length of 4. And if we were to plug 2 in here, it would be 12 minus 4, which is 8. So this would be a length of 8. And being very clear about what they're asking, what is the largest area? Well, that would be 8 times 4, which is 32. Units squared. I'll just say units squared. And also the dimensions are 4 by 8. So that is how you do number 11. Okay, problem number 12. Your ironworks has contracted to design and build a 500 cubic feet square base open top rectangle, blah, blah, blah. Tags to be made by welding, blah, blah, blah. What dimensions will minimize the material used? Okay, so I would draw some kind of a situation for that. And we know that the volume is 500 feet cubed. Let's see. And we also know that the base is square, so that's not really drawn to scale, but let's just work with it. Actually, it's going to bother me. It's going to bother me if I don't draw it to scale. So come on, geez Louise. I got to draw a square down there. That's what I should have done first. Actually, I could probably draw a square up top first, right? Hopefully that looks somewhat like a square. And then it's like this. Okay. So amazing. So therefore, we could call this, usually it's length times width times height. But I'm going to call this length times height. Because we know that that's the same as that, right? So therefore, the volume of this is going to be length squared times height. And we also already know what the volume is going to be. It's going to be 500 feet squared. So one thing's for sure, we know that L squared times H equals 500. That's going to be important information. Now, we want to know what dimensions will minimize the material used. Well, that would be a matter of getting clear on the surface area of this sort of structure. Let's keep in mind the top is open. So really what we're going to have is this base here, which I will literally call B for base. And then you're going to have this side, and you're going to have this side, and then you're going to have this side, and then you're going to have the purple side. So the area, or we could say the surface area of all that, is going to be the base, the square base, plus, now I think all of these sides are just h by L, isn't that right? H times L would give me this yellow side. H times L would give me the red side. H times L would give me the green side. H times L would give me the purple side. So then what that means is they're all the same size. So the sort of surface area is going to be the area of the base plus 4 times the area of each side. Okay. Now the area of the base we already know is L squared. Okay, I'll just write surface area, SA for surface area. The area of the base is L squared, and it's going to be plus 4 times the area of the side. Now the area of the side, once again, is L times H. Now, as I had alluded to in a couple problems earlier, we want to have 2 equations, typically, at least 2. One of the equations features the thing we're trying to maximize or minimize. Well, we're trying to minimize the material used, so that's going to be ultimately surface area. We're minimizing the surface area of the material used. Keep in mind, this is an open top here. So we're trying to minimize this, which means this is the thing we're going to take the derivative of. But then you always have to ask yourself, okay, do I have any annoying variables, like extra variables, when it's possible to work with only one variable? Well, yeah, actually, I'd say this H is the problematic one. We could substitute H in, stuff in for L, but since there's two L's and there's only one H, let's go on a separate mission to replace this H with something in terms of L. It's actually not a hard move to make because for my student at home, it's possible you already see it, that this one could be turned into H equals 500 over L squared. And we could also say that that is 500 times L to the negative 2. So what that means is that we could revamp this equation to be L squared plus 4 times L times 500 times L to the negative 2. And before proceeding, we could multiply 4 times 500. I believe that's going to give us 2,000. And then L to the positive 1 times L to the negative 2 is going to be L to the negative 1. So that's going to be L squared plus, again, 2,000 L to the negative 1. And at that point, we are ready to do the derivative. Okay, so I'll keep this, only we'll put a prime over it. So it's going to be 2L minus 2,000 L to the negative 2. And that would end up giving us, I'll write equals 2L minus 2,000 times L squared. Now, hopefully you remember that at that point, we'd have to set it equal to 0. And we could add this to both sides. We would end up with the blue equation. Now we're solving for L, so let's multiply both sides by L squared to get this L squared out of the denominator. We'd end up with, therefore, 2,000 equals 2 times L cubed. If we were to divide by 2, we'd have L cubed equals 1,000. And I think we could all agree, therefore, that L equals 10, which is very, very useful information. So L equals 10. And looking over here, we should easily be able to find out what H is. So H is going to be 500 divided by L squared. So that's going to be 500 divided by 100, and that's going to be 5. So my diagram is most definitely not drawn to scale. So there you have it. I mean, we have the dimensions at least. Yeah, so they asked for the dimensions. They did not ask for the volume. In fact, they gave the volume. But these are the dimensions that would minimize the material used. So one way of saying it is that it would be 10 feet by 10 feet by 5 feet. All right. You might want to hesitate to just be like, the length is 10 and the height is 5, because the truth is this is a three-dimensional object. Usually it's length times width times height, okay? But it just so happens that the length equals the width, so I just decided to call both of these the same variable by the same variable. But the teacher will probably want you to say something like 10 by 10 by 5. Length, width, height. Okay, so that's how you do that one. Hopefully that was helpful. I have another video coming up, and I will talk to you later. Bye.